In this presentation, I am going to explain previous GATE questions and answers for the year 2025, and the topic covered is electrical machines. Now let us see the question. 2025 GATE question that carries 1 mark. The operating region of a developed torque TEM and the speed omega of an induction motor drive is given by the shaded region OQRE. That is OQRE. That is the variation of electromagnetic torque with respect to omega. And the load torque TL characteristic is short. The variation of load torque with respect to omega is this one. This is a dark curve. And the motor drive moves from the initial operating point O, from this operating point O, to the final operating point S. This is the steady state operating point at the final point. Which one of the following trajectories will take the shortest time? The options are A, OQRS, OQRS. This is the final steady state point. Second option is OPS, OPS. Third option is OES, OES. And the fourth option is OFS, OFS. So these are the four options. Let us see this one. Now, there is a basic relation between the electromagnetic torque developed and the load torque and the accelerating torque. Therefore, the electromagnetic torque developed equal to the load torque plus J into d omega by dt. This J into d omega by dt is called the accelerating torque, which is equal to the difference of electromagnetic torque developed minus and the load torque. Therefore, here, once it is going to the steady state condition at the point S, TEM will be equal to TL, or J d omega by dt equals 0, or that is called the steady state condition. The accelerating torque will become equal to 0. Now, the question is that the operating point is moving from the initial point O to the S, which is the shortest time. That is, the shortest time will be taken if the motor follows the path that maximizes the accelerating torque. This is when it is maximum. J d omega that is maximum means that the difference should be maximum. That is the difference of electromagnetic torque developed by the motor and the load torque. If that difference is maximum, J d omega by dt will become maximum. That indicates that the time will be the minimum, or the shortest time will be available. And if you are looking to the different paths as given in this one, the trajectories which takes the shortest time will become OQRS. If you take OQRS, this is the final operating steady state point. Now, if you take this one, then there the maximum, the TEM by TL will become maximum, meaning that the accelerating torque will be maximum, or the time required for the minimum. For the answer for this problem is the option A, which is equal to OQRS. The path is OQRS. This is the final steady state point where the load torque will be equal to the electromagnetic torque developed by the motor. Therefore, answer is option A, OQRS. Now let us see another problem, that is 2025 GATE question that also carries 1 mark. The induced EMF in a 3.3 kV 4-pole 3-phase star-connected synchronous motor is considered to be equal and in phase with the terminal voltage under no load condition. On application of the mechanical load, the induced EMF phasor is deflected by an angle 2 degree mechanical with respect to the terminal voltage, and if the synchronous reactance is 2 ohms and the stator synchronous reactance is 2 ohms and the stator reactance is negligible, then the motor armature current magnitude in amperes during the loaded condition, that is for the 2 degree mechanical, corresponding to that, it is closest to round off to the 2 decimal places. Now, coming to the equivalent circuit of a synchronous motor, in which this is the applied voltage capital V, and here the back EMF EB is represented, and since we are considering only the synchronous reactance, therefore this is the synchronous reactance XS, that is the input side, this is the equivalent circuit, and here the field circuit, here the field winding as well as the field current is shown here. Therefore, this is the equivalent circuit of a synchronous motor, in which the corresponding the phasor relation is that the phasor vector, the applied voltage is equal to the summation of the back EMF and the drop across the synchronous reactance, EB plus IA into XS. Or we can say that one, the current IA is equal to V minus EB divided by XS. Now, if you draw the corresponding the phasor diagram here, see this is the terminal voltage, that is V here, and the corresponding the current, that is the current IA is, that is the phase angle of that one with respect to the voltage is called the power factor angle phi, that is IA, and the delta we have to calculate the electrical degree, we'll be seeing in the coming slide. Here mechanical degree equal to 2 degree, and for which delta means the phase angle between the terminal voltage V as well as the back EMF EB. That angle we call it as delta. Actually, we'll be calculating that one corresponding to 2 degree mechanical. We'll be calculating the coming slide. Therefore, this is the current which is lagging the voltage by an angle phi, and the voltage to EB, we have to add the drop across the reactance, then to get V. Therefore, the drop across the reactance is nothing but IA into XS. That will be perpendicular to the current. That is why this vector which is to be added with EB, that is perpendicular to the current vector, and this vector or this phasor we call it as IA into XS, the drop across the reactance. But the drop across the reactance is added with the back EMF to get the terminal voltage V. Therefore, this is a phasor diagram corresponding to the loaded condition of the synchronous motor. Now, continuing the same problem here, again this is the equivalent circuit, and here is a phasor diagram in which it's under loaded condition. But under no load condition, we know that one which is that the terminal voltage is same as the back EMF. Therefore, there is no drop across the reactance is equal to 0. That is why the terminal voltage will be same as the back EMF. In that case, the terminal voltage equal to or back EMF equal to 3.3 into 10 raised to 3 divided by root 3 into V. Now, synchronous reactance is it is given as 2 ohms, and when it is loaded, that mechanical the load angle is given as 2 degree, or corresponding electrical load angle equal to mechanical load angle into number of poles divided by 2. 2 degree into 4 divided by 2, or 4 degree. Actually, this is marked as the load angle, but this is not to the scale as in it, because it's not corresponding to, but just to make you understand that one, it's magnified and shown that one only, so not to the up to the scale. Anyway, the phase angle between the terminal voltage and the back EMF, that is the angle delta, which is equal to 4 degree. And if you write the corresponding the phasor equation, 3.3 into 10 raised to 3 divided by root 3, or that minus 4 degree, that is this one, this EB, that is equal to this one minus this one. We can write that one, or this is equal to the sum of this one, or 3.3 into 10 raised to 3 divided by root 3 into, or the phase angle equal to 0 degree, that minus this one, or JIA into the drop across the 2 ohms, or this is equal to the vector, that is what is this one, the back EMF EB. And if you substitute this one, which is getting, it is the armature, or that angle, that is IA equal to the current IA equal to vector IA equal to 3.3 into 10 raised to 3 divided by root 3 into phase angle 0 degree, angle minus 3.3 into 10 raised to 3 divided by root 3 into phase angle minus 4 degree. It is taken divided by J2, or we will be getting 66.49 phase angle equal to minus 2. Actually, this is also not up to the scale, but that is lagging the voltage by 2 degree. Therefore, the magnitude of this phase angle, so the armature current, that is equal to 66.49 amperes. Of course, there is a phase angle shift of minus 2 degrees. Therefore, the answer is 66.49 amperes. Now, let us see another problem of 2025 gate question that also carries 1 mark. The transformer connection given in the figure is a part of a balanced 3-phase circuit where the phase sequence is ABC. The primary to the secondary turns ratio is 2:1. That is, this is the primary circuit and this is the secondary circuit. The ratio of the turns is equal to 2:1. And if IA plus IB plus IC, that is balance case, then the relationship between, the question is that what is the relation between this current, line current on the primary, and IAD, the line current on the secondary? What is the relation between these two line currents, IA, I capital A, and IAD? So that is the question. The options are magnitude of IA divided by magnitude of IAD equal to 1 by 2 root 3 and IAD is lagging IA by 30 degree. Second option is that magnitude of IA divided by magnitude of IAD equal to 1 by 2 root 3 and IAD leads IA by 30 degree. Third option, magnitude of IA divided by magnitude of IAD equal to 2 root 3 and IAD lags by IA by 30 degree. And the option D equal to magnitude of IA divided by magnitude of IAD equal to 2 root 3 and IAD leads IA by 30 degree. Therefore, these are the four options and we have to analyze the circuit and we'll see in the coming slides. Of course, we'll see that one. Answer is option 4. Oh, sorry, answer is option A, but we'll be analyzing that circuit in the coming slide. Now continuing the same problem, let us see here already we have seen this is a primary circuit of a star connected and the delta connected secondary is the relation. What the question is that what is the relation between this line current as well as this line current? Magnitude of I capital A divided by magnitude of IAD. That is the question. And in order to find out that one, this IA, if you see that one, if this is a secondary phase current is equal to IA and this line current this line IA, of course, this line current IA, that is, and this, of course, this is the phase current, of course, IA, small IA. And here, this current corresponding the stator current that is equal to I capital A. Since these are the related by the ratio 2:1, this IA will be equal to this one, capital IA into 2 or 2 times IA. That is, these are in same phase. That is why this current is equal to, since the ratio equal to 2:1, I small a equal to 2 times I capital A. That's the first relation as such. Second, now let's see what is the IAD. In the balance case here, IAD equal to, of course, the magnitude of IAD equal to root 3 times IA. In a delta connected case, here this line current equal to root 3 times the phase current. Therefore, IAD equal to root 3 times small ia. Or small ia is equal to 2 times I capital A. For substituting that one, we'll getting 2 root 3 into modulus of IA. That is the current in the secondary side line current, IAD. Now, the relation that is modulus of IA divided by the, of course, the magnitude of IA divided by the magnitude of IAD. From this relation, it is equal to 1 by 2 root 3. Therefore, the magnitude of this one, the current through the primary, line current through the primary IA divided by this current IAD, that ratio is equal to 1 by 2 root 3. Next, we have to see the phase angle relation between this one. Now, coming to that one, this is the phasor diagram like IA, IB, and IC. And on the primary side, I capital A, I capital. Similarly, the secondary side also, that will be corresponding IA, small ia will be in phase to capital IA, IB will be in phase to capital IB, IC will be in phase to capital IC. Now, to find out IA, this current here, it is this IA equal to, what is that IA? We have to find out what is IAD. That is this current, we have to find out what is that one. Therefore, here the current, if you see that one way of representing this one here, this IA equal to this one current coming towards that one, IAD plus IC. Or if you apply the Kirchhoff's current law to this junction, current coming towards junction, IA equal to IAD plus IC. IAD plus IC. Or can say that IAD equal to IA minus IC. IA minus IC. Or you can say that IA plus minus of IC. Therefore, it is IA plus minus of IC. Minus of IC is added, vectorial is added. And then this vector is called IAD. Of course, this is a magnitude of vector which is already calculated. And the phase angle is equal to the angle by which this IA, the IAD is lagging, of course, lagging this vector IA by 30 degree. Therefore, IAD is lagging IA by 30 on the secondary side. Therefore, this is the primary side, if you look in that one, the same thing, IA and IA, I small a and I capital A, they are in phase. This one, these two are in phase. We have seen that this is lagging this one, IAD is lagging this IA by 30 degree, or meaning that IAD is lagging this IA by 30 degree. Meaning that IAD is lagging this line current on the star connected input, that is by 30 degree. Therefore, that is the phase relation between this IAD as well as IA. Therefore, the answer is that the ratio of this magnitude of IA divided by IAD equal to 1 by 2 root 3. We have seen that one. As well as the phase angle of IAD is lagging the phase angle I capital A of this vector by an angle. I mean this one will be lagging this vector by angle 30 degree. Therefore, the answer is option A. Now let us see another problem, 2025 gate question that also carry 2 marks. A series motor with a negligible series resistance is running at a certain speed driving the load, where the load torque varies as a cube of the speed. Or here the load torque is proportional to the N cube. The motor is fed from a 400 volts DC source and draws a 40 amperes armature current when it is starting. The case. Assume that linear magnetic circuit. The external resistance in ohms that can be connected in series with the armature to reduce the speed to the motor by half. Therefore, if say n is the speed at the initially, we want to reduce the speed to n by 2. Now, what should be the resistance that is to be connected in series to the series motor so as to reduce the speed to n by 2? That is the question asked. Therefore, the options are A 23.28 ohms, B 4.82 ohms, C 46.7 ohms, and D equal to no resistance is to be added. Now coming to this problem here, what given is that load torque is proportional to the cube of the speed. TL is proportional to N cube. And armature current, it is given as it is equal to 40 amperes. Armature current is equal to 40 amperes. In a series motor, as you know that one, since the field is in series to the armature, field current is also same as the armature current. Therefore, field current is same. And in that, because the flux is proportional to the IA, since the field winding is series to the armature, the flux will be proportional to the whatever the armature current. Then applied voltage is equal to 400 volts is the applied DC voltage. Since the series resistance is negligible, in the case of series resistance is negligible, here the back EMF will be same as the applied voltage. Therefore, for the back EMF is equal to, when it is running at a speed of n, the back EMF is equal to same as the supply input DC voltage, which is equal to 400, because the resistance is assumed to be negligible. Therefore, here the basic relation that load torque is proportional to the cube of the speed, and the motor torque, if you take that in a DC series motor, the relation between the torque produced by the motor, that is Tm, as well as flux and armature current, Tm is proportional to phi into Ia. Or meaning that since phi is proportional to Ia, Tm is proportional to Ia square. For a series motor, the motor torque is proportional to the square of the armature current, as well as it is given in the problem, load torque is proportional to the cube of the speed. At steady state, as you know that one, the load torque will be same as the motor torque. That is, this is the load torque and this is the motor torque or motor torque produced by the motor. Under steady state condition, load torque will be equal to the motor, the motor torque. For the at speed n, for example, at speed n, it is running at a speed of n, steady state at n speed. Then we can say that one, n square is proportional to the current square, because here Tm is proportional to Ia square at the speed of n, here not n square, n cube, because TL is proportional to n cube, or n cube is proportional to Ia square. When it is running at a speed of n cube is proportional to Ia cube. That is the equation 1. Since the in this case problem, Ia is given as 40 amperes. Therefore, Ia is the current that is corresponding to the, this is the current corresponding, this current 40 ampere is the current corresponding to the speed n. In that case, n cube is proportional to whatever the current square. That is the first relation. The second, when it is reduced to a speed of n by 2 here, now we have to calculate what is the current that's to be flown at the series to that series winding. Therefore, or Ia, what should be the Ia? When speed is reduced to n by 2, as per this equation, the load torque, if you say that one, load torque is proportional to n cube, or now speed equal to n by 2, or load torque is proportional to, of course, it is equal to n by 2 whole cube. That is, then that will be proportional to, okay, we don't know what is the current, because this is the relation between the armature current as well as the speed. These are the rated speed. Therefore, when the speed is n by 2, corresponding relation, that is what should be the value of the current. corresponding to n by 2, or n by 2 whole square is proportional to IA1 square. We have to find out what is IA1. Here the IA equal to 40 ampere, that is given in the problem, corresponding to a speed of n. Now corresponding to half of the speed, what should be the value of armature current? IA1 is to be calculated. From these two equations, if you dividing the equation 1 2 by 2, we'll be getting 8 equal to 400. Here substituting here 400 square divided by IA1 square. Here the current corresponding to the half of the speed is given by square root of 200 or 10 root 2. Therefore, the first step is that we are calculating, in order to run the motor to the half of the rated speed, what should be the armature current. We calculated it is equal to 10 root 2. And coming slide, we'll be calculating what should be the value of the resistance to be added in series. Now continuing the same problem here. Here we can see again n is proportional to EB by 5. The fundamental equation is, that speed is proportional to the back EMF divided by flux, or n is proportional to, since the flux means that in the series motor, that is IA is proportional to, of course flux is proportional to IA. Therefore n is proportional to EB by IA. Of course, when speed running at speed of n here, it is taking a current of 40 amperes. And the corresponding EB, that is EB is proportional to 40N, or the corresponding EB, as you know, that is already calculated 400. 400 is proportional to 40 into N. Now when the external resistance, in order to reduce the speed to half of the one, we are adding an external resistance. R external is connected to reduce the speed to N by 2. Under that condition, again if you apply this equation, or this N proportional to EB by, that is EB is, in that case, EB is given by, since we are adding a resistance here, EB is given by the voltage, terminal applied voltage minus the drop across the resistance, IA1 into R external 1. That is proportional to corresponding, of course, here that is equal to, as per this equation, we can say that one. That is, I am taking this one as product of that one. That is equal to the IA1 into N by 2. Or here, 400 minus IA1 is calculated as 10 root 2 into the external resistance is proportional to IA1 10 root 2 divided by 2 into N, or N by 2. Or this is from these two equations, only the unknown is R external. Or you can say that one, equation 4 divided by equation 3, 400 minus 10 root 2 into R external divided by 400 equal to 10 root 2 divided by 2 into 40. Or solving this one, we can get what is the external resistance to be added, which is equal to R external equal to 23.28 ohm. Therefore, if you are adding a resistance of 23.28 ohm series to the series, series motor, then the speed will be reducing from whatever the speed at N to N by 2. Now let us see another problem, 2025 gate question that also carry 2 marks. A 3-phase 400 volts 4-pole 50 Hz star-connected induction motor has the following parameters referred to the stator. Referred to the stator, it has the following parameters. That is, it is the rotor resistance referred to the stator, RR dash, which is equal to 1 ohm, and the stator reactance, which is equal to the rotor reactance referred to the stator, or the XR dash, which is equal to 2 ohm. The stator resistance, magnetic reactance, and core losses of the motors are neglected. The motor is run with a constant V by F control from the drive. The maximum starting torque, the voltage, and the frequency output respectively from the drive is, what is the corresponding to the maximum, for the maximum starting torque, what is the voltage as well as frequency, V by F control we are using. What should be that one? What is that one? Drive closest to that one. The answers, the options are 400 volts and 50 Hz. That is voltage 400 volts and the frequency 50 Hz. Second option is 200 volts and 25 Hz. Third option is 100 volts and 12.5 Hz. And the option D is 300 volts and 37.5 Hz. Now let us analyze the circuit. Therefore, the equivalent circuit of this induction motor is drawn here. And here, this is the input voltage is marked as V, and this is the JXS. It is the stator reactance per phase. It is drawn here, and this is the rotor reactance referred to stator, and this is the rotor resistance, that is RR dash is the rotor resistance referred to a stator, or R dash divided by S is the load as such. Therefore, this is the per phase diagram of an injection motor. Now, the rotor resistance referred to the stator is given already in the problem. It has 1 ohm, that is 1 ohm. And at 50 hertz, we have seen XS equal to XR. That's given in this problem. At 50 hertz, XS equal to XR dash, which is equal to 2 ohm. XS means that 2 pi into F, frequency 50 into what is the inductance LS, which is equal to 2 ohm. Similarly, for this rotor side, rotor reactance referred to a stator, that is equal to again 2 ohm, which is equal to 2 pi into 50 into LR dash equal to 2. Now, if you solve these two things, we'll be getting what is the inductance of the stator side as well as what is the inductance of the rotor side referred to the stator. Therefore, from this relation, we can calculate what is the inductance of this stator, that is LS, that is same as the rotor inductance referred to the stator, that is LR dash. Both are same here. 2 into 2 divided by 2 into 2 pi into 50, which is equal to 6.369 millihenry. So that is calculated. And the next slide we'll be continuing this. Now, the question is that at maximum starting torque, what should be the voltage magnitude as well as the frequency, since we are using a V by F control. Therefore, let the frequency corresponding to the maximum torque is represented as Fm. And under maximum starting torque condition, total reactance is equal to the resistance. That is the condition to be applied. Therefore, XS plus XR dash corresponding to the maximum starting torque, that should be equal to RR dash, or which is equal to, we can say that, which is equal to 1 ohm here. XS equal to 2 pi into Fm into LS plus XR dash means 2 pi Fm into LR dash. Already we have found out LS and LR dash in the previous slide we have that calculated. And that should be equal to the resistance. That is the condition to be satisfied to get a maximum starting torque, which should be equal to 1 ohm. Therefore, substituting here, the only unknown is Fm, because LR dash as well as LS already we calculated. The only unknown is the Fm. From this equation, Fm can be calculated as 1 by 2 pi into LS into LR dash. 1 by 2 pi into, already we calculated LS and LR dash, is equal to 6.369. Already we have calculated. No, it is equal to 6.369 millihenry. Substituting that one here, 6.369 millihenry here, then it will be getting 12.5 hertz. So the frequency required to get a maximum starting torque, that should be equal to the 12.5 hertz. Now, since we are using a V by F control, that ratio of V by F should be constant. Therefore, when the voltage equal to 400 volts, the corresponding frequency was 50. Therefore, 400 divided by 50 is the V by F. That should be equal to, here you have to find out what should be the voltage, because frequency required equal to 12.5, already calculated. Therefore, that voltage divided by 12.5. From this equation, the only unknown is what is the voltage corresponding to the maximum starting torque. For the voltage corresponding to the maximum starting torque from this equation equal to 400 into 12.5 divided by 50, or is equal to 100 volts. Therefore, hence the voltage and frequency of the drive, in order to get a maximum starting torque, it is equal to 100 volts, 12.5 hertz. Therefore, the answer is option C.